In this second video on the trapezium rule, we're going to look at the general formula for approximating areas using trapeziums. It's a really useful technique because sometimes integrals can be very complicated to work out, whereas trapeziums are maybe computationally large but are simplistic in principle to work out. So the general picture I want you to imagine is that you've got this red curve here, maybe a quadratic, maybe something much more complicated. And we can approximate the entire area under that curve with trapeziums. And the key idea is that the more trapeziums you use, the better your approximation. We can see when n equals 1, we're missing out a lot of area. This is quite a poor approximation. When n equals 2, where instead of doing one trapezium, we use two trapezium to fill that gap, we get a slightly better approximation, certainly less blank space here. And as we do more trapeziums, we get a much better approximation. In that final one, for n equals 6, we can see that the trapezium area and the area under a curve are almost indistinguishable from each other. Let's focus on that error a little bit more though. I can think of two errors that we could come across. Some of the time we are going to overestimate the area. This will occur when the curve is convex, when the actual trapezium includes more area than the area under the curve does. However, there's a flip side. Sometimes we will underestimate the area. And this will occur when the curve is concave, because now we've got too much. We've got an added area here that is excluded from the trapezium. In a similar way to our previous example, we can think about what would happen if we split the area under a curve into n trapeziums. So we would start from A, we'll call that the starting x coordinate, x0, and we would have xn as the last one for B. And we'd split it up into trapeziums like so, x1, x2, and then dot 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 until the last one. But to work out the area of trapeziums, we also need to know the y coordinates. So when x0, we would have a corresponding y0 for x1, a corresponding y1. For each value, we'd have a corresponding y value. And in our formula book, we are given the following formula. The area under the curve, which is the same as the definite integral, can be approximated, not exact, but approximately equal to h/2, and then adding the two endpoints only once, but for all of the middle trapeziums, for example this one and this one, their y ordinates get added twice, once for each rectangle. And we've even got a formula for the width of a rectangle. It's given by the total distance b minus a divided by the number of rectangles n. And there's one thing I really want to draw your attention to here. In this diagram, we've got n trapezia, but there's actually n plus 1 ordinates, because we've included x0 as an extra and y0 as an extra ordinate. So to summarise, there will be n trapeziums, but there'll be one, which will be one less than the number of ordinates, the number of y values. And this formula really speeds up the calculation we did in the last video. We can see it's the same problem. We've got a definite integral, So we're trying to work out the area under a curve. And I've just replaced this formula. Instead of going up to yn, I've stopped at y4 here. Being careful to add the two endpoints once and every other ordinate twice. So we just got to finish off this table calculating each value. We're just going to substitute in when x equals 2, y equals 1 over 1 plus 2 squared, which equals 0.2. Similarly, when x equals 3, y equals 1 over 1 plus 3 squared, which equals 0.1. And then to work out the width of each trapezium, it's this part of the formula here. H equals b minus a over n. But there are 1, 2, 3, 4, 5 ordinates, but one less for the number of trapeziums. If you think about our picture, there is only a trapezium in between the gaps of each number. So there's only 4 trapeziums. So h would equal the total x distance, going from 1 to 3, divided by the number of trapeziums, 4, which equals 0.5. And then plugging into a calculation, we get the following sum. Can't write, beg your pardon, 0.5 for h over 2. y0 is also 0.5 plus y4, which is 0.1. And then times in all the middle ordinates by 2. Which equals 0.473. Which is the same answer we got in our previous video, but the formula speeds up the calculation. Let's go through another example. In example 6. We've got a new curve, y equals 2 to the x, and we're asked to find the area between 0 to 2 using 8 strips. So in that formula, I've replaced n with 8, and it's now time to find out the different coordinates to insert into our table. Well, our starting value is going to be x equals 0, and our finishing value will be x equals 2. There are 8 strips in total, so to work out the width h of one of those rectangles, it's the total x distance, which is 2 minus 0, divided by the number of trapeziums, which is 8. 2 over 8 equals 0.25. So our x coordinates come in regular intervals of 0.25 in particular. 0.25, 0.5, 0.75, 1, 1.25, 1.5, 1.75 and 2. And then for each number, substituting in to our value, I'm going to leave it in exact form this time, just to save on the calculation. We would get 2 to the 0, which is 1. 2 to the 2.5, so 0.25, and so on and so forth. And substituting into the formula gives this calculation. Oh, forgot my last one. 2 to the power of 2 is 4. So h over 2, 0.25 over 2. And then writing out each of those numbers, 1 plus the last one 4, and then 2 times all the middle. And grabbing the calculator out, we get a long decimal which rounds to 4.34 to 3SF. So the formula was really key to that calculation. We had to take our time to work out the width by dividing by the number of trapeziums and then times in by 2 the middle ordinates. Let's analyse question B to find the reference to a sketch of y equals 2 to the x, explain why it is an underestimate. Well, I've just drawn the curve, the exponential curve, y equals 2 to the x here. And I've just tried to visualise exactly one of those trapeziums. And we can see that there's some extra area on top there. That red area is not included with the area under the curve, which is what the integral finds. So it's an overestimate since each trapezium has additional area above y equals 2 to the x, because it's a converse shape. I beg your pardon, it's not converse, it's not the phrase I meant to say convex. So since each trapezium has additional area above y equals 2 to the x, it is an overestimate. Nice. We've done 2 examples there using the trapezium rule. In our next video, we'll look at the effect of transforming graphs on trapeziums.